the theme is sort of, beyond topological phases, I think. Okay.
Beyond or
behind? Well, so let me start with like a little recap of what we did last time. So the kind of basic take-home message of last time's lecture was that, we have, of course, topological phases, such as, for example, the toric code, which we can write down as an explicit Hamiltonian. And there we could see that it has a ground state degeneracy and it has, excitations with some interesting braiding properties. But we also have these sort of topological like phases, which I'll call sort of in general fracton phases. And these come from, so the examples that I wrote down come from constructions. These were also constructed in the physics literature, but there's a very general family of constructions known as CSS codes, and that basically means that you have, in both cases, some vertices, and I have terms at vertices, and I have terms on plaquettes, or, cubes in 3D, okay? And these guys involve some product of sigma x's, okay? And these guys involve some product of sigma z's, okay? And I gave you some examples that are sort of toric code-like, okay? And they're toric code-like, first of all, because, the Hamiltonian has this same form everywhere. And we showed that they have, so two kinds of particles, right? So the particles that live at vertices, we can call them E particles in general. And the particles that live on plaquettes or cubes, maybe we can call them M particles in general. And we showed that these always have, whether I was in, 2 dimensions with the toric code or maybe in 3 dimensions, right, that E's and M's are point particles, okay, with some kind of mutual statistics, which we saw from the fact that if we looked at, operators that create E's and operators that create M's, they don't commute, okay? And we showed that there's a sort of like a general, or I sketched why there's a sort of general BF theory description at least I sketched it in one case and maybe sort of implied that you might want to think about it as being more general. And the reason for that is that basically this condition here, right, we can think of a constraint, we can think of this as a sort of Gauss's law. And this condition here, we can think of as a constraint. Oh, this is really let me write phi for magnetic flux is equal to 0. Okay. Okay. But there are some important differences when we go sort of beyond topological order. And from the point of view of sort of hiding quantum information, one of those differences is that you have a lot more ground states, okay? So these guys all had families of locally indistinguishable but nonetheless distinct ground states, okay? But in these fracton phases, I have many more of them. And the reason for that, in some sense, can be traced back to the fact that the particles here have restricted mobility. And let me just kind of remind you of how and now I want to say, maybe just in this simplest case, I'm going to maybe give a slightly different explanation of how this works. So one of the models that we wrote down had you know, spins on the plaquette centers and on the edges. And when I wrote down a BF theory for this model, I said, well, maybe we could think about a U1 version of our gauge fields, and we would have an AXY, that's the natural thing that lives at the center of a plaquette, and an AZ that lives at the center of an edge, okay? And the gauge transformations for AXY, again, if we take it to be a U1 gauge field with U1 transformations, okay, then, okay, and I should say, yeah. Uh-huh. Mm-hmm. Yes.
And so you would have expected naturally AXY to be an anti-symmetric function, not a symmetric function.
Ah, okay. Yeah. So
This always puzzled me why here, what is done that makes this always symmetric.
okay. Yeah, okay, so let me write down the gauge transformations, and I hope this will address this question. Okay, so the natural sort of thing to think about here, so what I'm going to do is I'm going to talk about this field AXY, I'm going to write down the gauge transformations, and then we're going to see why that choice of gauge transformations is related to having particles with restricted mobility. You have a question? Yeah.
So another example of the same thing is like in gravity, you have a metric, which is symmetric, and still you can understand it with having Riemann tensor, which is asymmetric with the single strength, and there is a gauge field, which is the. So what I'm saying is that this.
But it's a fourth rank tensor.
I know, but I'm saying that this AXY, I think you should interpret it more like a symmetric than as a gauge field.
I understand that too, but if I just simply think of a plaquette, okay, fine.
So.
That's what I am confused. I mean, so you could think of that as gravity, maybe fine.
Exactly, yeah. Well, it's the connection that you guys read for this.
Okay. So, well, first of all, let me maybe make sure that we're all on the same page of, what's sort of symmetric about this. Well, one of the things that's symmetric is the gauge transformations, okay? So under gauge transformations, I imagine that I put matter fields on the lattice at the four corners of the plaquette, and I have a gauge transformation under which the matter fields, transform with the U1 phase in this plus minus kind of pattern, okay? And if you work out what this means for AXY, it transforms like delta X, delta Y alpha, okay? So this is, obviously a symmetric representation of a tensor gauge transformation, okay? Now, with this gauge transformation, okay, we can sort of explicitly look at, okay, so now I'm just going to represent, this I'm going to write as plus, and this I'm going to write as minus, and we can ask, well, what are the gauge invariant operators, okay? And certainly, I can take a line of plaquettes, right? Because on the line of plaquettes, here I have a plus and a minus, and a plus and a minus, and here, right? And so I can see that, at each vertex I have a plus and a minus, okay? So this straight line is, gauge invariant if I wrap it around my system, for example, or maybe I have matter fields at the ends. There's a dipole at the end, okay? However, you'll notice, right, that if I tried to make this line of plaquettes turn a corner, so maybe I try to do this, okay? So now my gauge transformations look something like this, right? And so I'm almost okay, But you can see that there's a corner left over, and that would mean that, basically, if I tried to turn this ribbon operator, okay, and you can also see this explicitly if you sort of look at the Hamiltonian terms that I wrote down last time, that if you try and take an operator that wants to create a dipole and you make it turn like this, okay, you're going to have to to make this gauge invariant, you're going to have to put a matter field here. When I come back to this model, what that's going to mean is I'm going to have some kind of excitation living at this corner, okay? So the first observation is that this symmetric choice of gauge transformations forces my gauge invariant operators to be these straight sort of ribbons, okay, in the xy plane. Now in the z direction, right, this is like an ordinary rank 1 gauge field, so the lines in z are just lines, okay, and now I can take a pair of lines in z, right, and I can wiggle this around in the z direction, which is, why we call them planons. These dipole objects can move around in either the xz or the yz planes, okay? I have these, gauge invariant ribbon loops, but they can't turn between xz and yz planes. Okay, now, so here, right, so Wilson lines, right? So what am I allowed to have? I'm allowed to have some integral of az dz, right? Or I can have these ribbons, right? In the xz or yz planes, and these are sort of these ribbons of dipoles. So that's the analog of Wilson lines in this model. Okay. And so, the fact that the Wilson lines can't turn the corner, that's sort of giving us our restricted mobility. There's another, I think, kind of appealing way to think about that, okay? Which is to make a connection to a model with a global, okay, what we call subsystem symmetry. All right? And so I'll explain what this means in a minute, but let me just, start by supposing that I'm going to add a current. Okay? And obviously, I can't add a 3-component vector current. I only have 2 components of my gauge field. Okay? So the natural thing to write down, well, I have A0, so we'll couple it to the charge density, as usual, right? And I have AZ, and we know what AZ couples to. It couples to some current in the Z direction, okay? And I also have AXY, that's my other component of the gauge field, so we'll just couple it to some component of the current, which we'll call JXY, okay? And now we can ask, okay, if I couple my gauge field to a current in this way, and now I'm going to perform some, now the current better be gauge invariant, okay? So I want to add this term to my action, and I want to preserve gauge invariance, right? So, and by the way, just like people who are past about the 2nd or 3rd row, I'm blinded by the lights, so if you have your hand up, I probably can't see, so just, if you have questions, please just shout, because it's a little hard to see up there. Okay, so now we can ask, well, what happens to this coupling under gauge transformations, right? And so here are our gauge transformations, which have some parameter alpha. And now, look, in the continuum limit, okay, this is going to become dx dy. So I'm just going to use continuum notation here. It doesn't really matter. You have to be a little bit careful with the coupling constant, with the taking the continuum limit, but basically you can do this. All right. And now So let me, so this is equal to my original A mu, J mu piece, right? Plus dt alpha rho minus dz alpha jz plus dx dy alpha jxy, okay? And now you can see why I've sort of made this funny choice of sign here. So if I ignore boundary terms and I just integrate this by parts, I get an alpha, I get, we'll put the minus sign out front, dt rho minus dz jz minus dx dy jxy. Okay. And so this is sort of my, right? So then, obviously what gauge invariance requires is that this quantity here has to be 0, right? And so the analog of current conservation in this case tells me that dt rho is equal to dz jz plus dx dy jxy. Okay. Good. So now we can ask, so usually, right, when we have a conserved current, right, we can show that we have some kind of like charge conservation when we have a closed system and we look at the whole system, right? And let me just remind you, right, the usual case tells us that dt rho is equal to grad dot j, okay? And so that would tell me that if I take, so I'm going to take the time derivative of the total charge in my system, and by that I mean the integral over some closed manifold. Okay, we're not going to deal with boundaries right now. So integral over a closed manifold of dt of the charge density, right? And then, of course, that's just the integral over a closed manifold of grad dot j. But this is a total derivative, right? And so this is 0, and so this tells me that my total charge is conserved. And here, we can make a similar argument, okay? Except we notice that, if I take the integral over, say I put my system on the 3 torus, okay, now I have to be a little bit more careful about what manifold I choose, okay, whoops. Okay, but let's suppose that I have periodic boundary conditions in X and periodic boundary conditions in Z, okay? And if I take the integral of dz jz plus dx of dy jxy, right? Well, again, this is a total derivative, and this is equal to 0. And similarly, if I take an integral over y, right, of this same quantity, I also get 0. So that tells me that I can define, actually, for every value of y, I can define a conserved charge. And similarly, for every value of x, I can just define a conserved charge, right? And so basically, in this theory, when I kind of globally take the continuum limit like this, okay, And really to match up with the Wilson line operators, I should, I could integrate this a little ways in the y direction to get a ribbon. And if I was being careful about matching the lattice to the continuum, that's what I would do. But this gives me conserved charges, right? And this is, so this tells me that the current that I've coupled to this gauge field was a current that had, it started off with some conservation law, which wasn't global charge conservation, it was actually charge conservation, right, in each of these. And, like I said, on the lattice, these things are a little bit thick at the level of the lattice constant, right? But I have a, this is some number y here, and this is a qy, okay, and this is conserved. Okay. So basically, I think one way to think about this is that when we write these symmetric tensor gauge theories, okay, which involve, this particular combination of second derivatives, we are naturally led to mobility restrictions, okay? You can also sometimes have this with anti-symmetric tensors, but the simplest ones, okay, the simplest ones, just these AXY, happen to be symmetric. And so this is, and so it is, it's different. It's different. Okay. Good. All right. And so this is sort of, another connection, right? And there's this kind of general observation that quite generally, these sort of fracton orders that we know about can be obtained by gauging some kind of subsystem symmetry. Okay? And this idea was originally proposed in a paper by Vijay Ha and Fu around 2016. And they used it actually to construct a bunch of models that hadn't previously been known. Yes? Sorry, say it again? Yes, right. So these charges all commute in this case, yeah. So we'll get to a situation where that's a little more subtle in a few minutes. Okay, good. So, just to say, we have these families of models. They have topological-like properties, okay? But they have this restricted mobility, okay? Restricted mobility is connected to the notion of having a weird kind of global symmetry where instead of having, charge conserved in the system as a whole, I actually have a lot more conservation laws. And, and it's sort of once I have more conservation laws and I gauge the system, you can think of that as the reason that I get more indistinguishable local ground states. Sorry, locally indistinguishable ground states. Okay. So maybe I'm going to kind of end this part of the talk with some questions. Yeah, good. So the question is like, is this model really different from a stack of two-dimensional things? And I would say that it is, and maybe I can draw a picture of that. So, what are the statistics? So here, let me just, this is maybe a computation that's easiest to see the level of the lattice model, right? So here was AV, right? It had x's on these 6 guys. And then, the cube term, this is BC, okay? And it had z's on these 6 places, okay? And so now we can ask, so an E particle is created either by, right? So I can act on these vertical edges, right? Here's a plane with a bunch of z's, right? Or I can create sort of a pairs of e's by acting with z's in the plane, okay? So we have sort of these z ribbons or sheets, okay, and in the xy plane, and these z lines. And if I ask what kind of thing is creating M, well, I see that to create an M, what I need to do to move the M vertically, I have a string of X's, those hit the plaquettes, right? And then if I want to move them in the plane, right? So in the plane, I want to hit, a single X will create 4. So if I make a pair of X's, right, on 2 edges, I can again make this ribbon in plane, okay? And so now we can see, and let me just kind of sketch, maybe I'll make these guys red so that we can tell who's who, right? So let's make the Z ones red, okay? And so now I can sketch, so, let's suppose that I have a Z particle sitting here, okay? And then I want to bring my X particle around it. This is the braiding statistic, right? And so I have this sort of forest. I'm going to represent them with a single line, but each of these, right, if we're looking straight on in the plane, each of these, what it looks like is, of course, it's a pair of, parallel edges, right, on each side of the plaquette. So this is my ribbon, right? This guy only has a single edge, so there's a single edge on which these guys hit, right? And now I'm gonna, and now I have my dipole, right? So now I can move this with a plaquette, and I can go, right? I can go down, right? So I have this sort of tower of plaquettes, and then I can sort of bring it back across on the other side and close it up, okay? And so this is really there's a 3-dimensional nature to the statistics, and so I think that's a nice way to understand why these really are not stacks of 2D systems. Okay. Yeah, so this model, right, so in many fracton models we have like dipole conservation in all directions. In this model, of course, like the dipole moment in Z is not conserved because these particles can move up and down in Z. But yeah, so dipole moment conservation, basically the fact that the fact that the charge, so the fact that the charge in each of these XZ and YZ planes is conserved basically gives me, not only that, so that means that these dipole moments in the XY plane are conserved, okay? And it's even sort of a stronger version, so if I looked at my dipole going this way, if I just wanted to conserve the total dipole moment, there's sort of processes, coordinated hopping processes that I can do, and here, like really, this is very strong. I can't really move anybody. The dipole's kind of rigid. Yeah. So, well, okay. So here's the sort of the crude picture. Let me just draw a 2-dimensional picture, okay, of our XY plane, okay. And now, if I told you, so in this 2-dimensional projection, I sort of projected all Z onto this one picture, right? And I told you that basically, the total charge along each of these lines is conserved, right? So basically, so that means that, if I have and also the total charge along each of these lines is conserved, okay? So these conservation laws of the total charge along each line imply conservation of dipole moment. Yeah, it's sufficient. Sufficient, but not actually necessary. Yeah, good. Okay, so I want to end this section with a couple of, sort of questions, and there's quite a bit of work on these questions, and I'm not going to go into the details, but maybe this is just to sort of pique your interest about what you can think about for these Fracton orders, so topological order, beyond topological order, okay? And so the basic question is like this. So we know that for the toric code, right, the toric code is one very simple instance of a vast family of phases of matter that we can write down, right, which are two-dimensional topological orders, right? And there's many things that are qualitatively not like the toric code in this family, right? So we can write down Chern-Simons theory, right, which has a central charge, maybe ungappable edges, right? We could write down sort of what are often called Dijkgraaf-Witten models, or twisted gauge theories, and I'll give you an explicit example of this in a minute, so don't worry if you haven't heard about this, but these are models with c equals 0, but self statistics. Okay. And of course, I can write down all kinds of fun and exciting non-abelian stuff. Okay, where I have point-like particles that are non-abelian, and I can braid them around, and this is as I alluded to last time, this is maybe a nice place to hide quantum information, particularly if you want to imagine making some kind of building a sort of qubit using topological phases. And so this analogy between the toric code and things like this line-on-plane-on model sort of begs the question, how much of this, let's say it like this, how much of this also applies to fractons, okay? So as I said, I'm not going to go into detail, but I'm going to make two comments. Okay? So the first comment is that to make these things non-abelian in a kind of really, say, three-dimensional or higher than two-dimensional way, is sort of tricky, okay? Now, there are many constructions, or some constructions, that do have a non-abelian type character, okay? So there's, and here I forgot to write down the full author list, but there's various constructions. One is called a CageNet model of fractons, or sort of coupled layer constructions where you take layers of topological orders and couple them together, okay? There's also constructions where I can have something like non-abelian defects, okay? But there's a basic reason that it's a lot trickier to get non-abelian stuff in the context of fractons than it is in the context of 2D topological orders. And it has to do with the fact that these subsystem symmetries so the symmetry that we're gauging to get this model basically wants to be abelian. Okay? What do I mean by that? Well, again, let me sort of project into a 2D plane, right? So here we have subsystem symmetry in the xy plane, and then just, the z direction doesn't have this conserved dipole moment, okay? So if we project this into the xy plane, so let's suppose that I had a non-abelian group, okay, and I had something like this subsystem symmetry in the x direction and the y direction. And so maybe I could act with G along this line here, and I could imagine acting with H along this line here, right? And I could do this and undo this, and that would imply that, you know, at this point, which is really a line in the z direction, okay, I can create just a point operator, okay? So basically, if the group is non-abelian, right, if the group is abelian, this is the identity element, obviously. But if it's non-abelian, then I start to generate, right, I generate lower dimensional symmetries, right? So in this case, a symmetry along just a line in the z direction, okay? So although, you know, as I said, there are definitely constructions that have some non-abelian character to them, you know, I think what we can do with non-abelian stuff over here is definitely more limited than what we can do with 2D topological orders. I think the full extent of what we can do with non-abelian stuff is maybe not completely understood. Okay. So let's table non-abelian things, and let's ask, well, what about Chern-Simons terms? Yeah.
So what is the problem, like the first principle problem with having that point particle there?
Right. So here it's just that I started with a model where I just wanted, you know, charge conservation along these planes, and now I have a model where I have some charges that are like really conserved along lines. And so I'm not saying you can't think about these models, but I'm saying that, you know, the way that the excitations sort of move around in these models is going to be different. It's not just the obvious generalization. And like I said, you know, and then you might say, well, you know, in 2D, like non-abelian things don't have to come from groups, and maybe there's other things that are not group-like that are more naturally non-abelian. So there's a space of things to explore, and there's definitely some work on that. But I would say that, and so I would say we just don't have a definitive answer to exactly what are the constraints on, you know, how non-abelian these things can be. Yeah. Okay. So now comment 2. Okay. What about like abelian sort of Chern-Simons type terms? Okay. And so let me remind you that let me remind you of what the BF action is, right? So you might say, and I'm going to talk about this specific example, but there's a sort of general theme here, you know, at least in 3 dimensions that I'll try to pull out, okay? So last time I wrote down a BF action, you know, that I said just captures the, you know, the constraints from these 2 terms. Did I erase them? I already erased them. Okay, from the 2 terms, you know, AV and BC and this Hamiltonian, right? Now, caveat, when I wrote, I'm going to choose a different sign convention last time than I did last time. Last time I used a sign convention that was from the paper by Shirley, Slagle, and Chen. Okay, today I'm going to use my own sign convention, which is slightly different, but nonetheless also gauge invariant, which you can check explicitly. Okay. And so if you compare to your notes from last time, that's why. Okay. So you might say to yourself, well, okay, we have this nice BF term. So maybe I can write down a Chern-Simons term, okay? And you can check, by the way, that, so, you know, the signs here have to be chosen in a particular way for the action to be gauge invariant, okay? So that's important. So you know, I can't change the signs around here willy-nilly, or it won't be gauge invariant in the bulk, okay? So you might ask yourself, well, you know, a natural guess for a Chern-Simons action would be that I should just replace the B's with A's, right? That's what we do in 2 + 1 dimensions, right? And let me start by I'm going to start by sort of writing down a naive continuum limit here, okay? So, okay. Ah, sorry, these are A's. Yeah. What's wrong with this action? Can anybody tell me? It's 0. Yes, yeah. So the problem with this action, the reason that this is not a good choice is that it's 0, right? So you can check that, or it's a total derivative, okay? And that has to do, you know, basically I have some terms with 2 derivatives and I have to choose my signs in the right way so that it's gauge invariant. And when I do that, you can see that actually if I replace B with A, I get a total derivative, okay? And so the sort of obvious thing to try to do is to say, well, okay, this was a total derivative because of some stuff that happened by integration by parts. Okay, so let me write down just, you know, an obvious thing you might try, which is that, so you can fix this problem by sticking in an extra derivative here, okay? So, and I'm going to call the coupling constant A for reasons that will rapidly become apparent. So I'm just going to pick some direction, which is going to be, in this case, you know, it's a kind of a convention. It's going to be the x + y + z direction. Okay, and I'm going to stick in a derivative of that. Right, in front of all of these terms. AZ. Okay. And now you can check that so right now I'm just saying, like, let me try and write down a continuum action. And I'm just, you know, saying at a naive level, here's something I might try. I could choose, for example, this dn to be, you know, dx plus dy plus dz. Okay? And so now, this action is not 0. You can check that. Okay, it's no longer a total derivative. It's also gauge invariant. So these two things are desirable. But of course, I had to stick in this extra derivative relative to my BF term, right? So this coupling constant, which I've suggestively named A, is dimensionful. It has units of length. Okay. And, I think there's different ways to think about this in the continuum, and you might say, that in the continuum, that just means this term is 0. But I think one way to think about this is that, so you can certainly write a term like this on the lattice, okay? And it just involves, instead of, so if we come back to the lattice, I have to couple, so A0 lives at the vertices, and I have to couple it to, this term, this cube term, which is sort of what we're calling this B cube, which is, involves a bunch of A fields, and it's centered at the center of the cube. And this choice basically amounts to coupling both of these guys to this B, okay? So it's an allowed choice on the lattice. And you might ask, and so let me say that, this I'm sort of sketching for you, but if you want details of a example with slightly different gauge fields, okay, where the calculation is done in more detail, okay, then there's a paper by, Yiji was first. So details can be found in a paper by Yiji Yu, Trithep, Devakul, Shivaji Sandhi, and myself on sort of Chern-Simons and BF theories for these models. And, the basic, so this is a different model, and I didn't want to get into the geometry of that model, okay, but for those of you who know, we wrote down something that describes the Chamoun code, okay, essentially. And the interpretation is basically, I think, the same, right? That why is it that actually, should you think of this Chern-Simons term as problematic? Should you think of it as something that is, kind of not meaningful because it has this dimensionful coupling in the continuum limit? And I think if you go back to the lattice, right, this is sort of telling you about the fact that the kind of statistics, okay, that these theories describe, and I'll come back to this a little later, is it's a statistics, gosh, this is a terrible picture. It's a statistics okay, of essentially objects that we should think of as lattice scale dipoles, okay? So in this model here, and I'll say more about this next time, the statistic is between, so here's sort of a dipole in the YZ plane, right? And it's gonna live, a dipole that's mobile in the XZ plane, right? And it's gonna sort of extend from this value of Y. And the kind of statistics that this theory describes, and I'll explain this more next time, is a statistics between this dipole and one that's sort of sticking out of the plane in this direction, okay? And so the fact that these are extended objects in the other direction is actually important for getting out the statistic, and that's why the coupling constant is dimensionful. Okay. Good. Any questions about this? No? Okay. Yeah. Yeah. So when you do the sum and difference of what? Oh, yeah, yeah. You're left with only here. Okay, this I haven't thought about, and I'm not sure if I can do it live. Do you have a comment?
Maybe it's related to that in some way. now you are basically doing the contrary, doing the F for the A and the
Yeah, that's right. That's right.
derivative. I mean, you put the derivative is like a stereo derivative, no?
The derivative is
That derivative can be thought as a stereo derivative or not?
as a which?
As exterior derivative.
As an exterior. Oh,
So that I can think now that you are doing like dA.
okay. You're right.
So it's not really a change sign on them. It's like again a kind of dual DF term.
Oh, you're asking about like the connection between the A's here and the B's here. Yeah, okay, so here, I mean here, when we go, so, you know, remember like, here the B's very much live on the dual lattice, right? So, you know, on this plaquette I have AXY, and then I have BZ, which lives on this plaquette, and this has to do with the mobility. So like at the lattice scale, right, and then the idea is, you know, now when I want to, you know, say I look at this term, right, and now to go from here to here, what happens at the lattice scale is I have to pick, you know, I have, so before, right, I had these, the BXYs were living on the edges, okay? So if I took, and you know, and B naught was living, B naught was living at the center of a cube, and you know, BZ was living on this edge that pierces the plaquette. So there's a natural pairing, right? And now when I want to do this with like A naught, right, I have to sort of choose like, well, which edge does this guy talk to, right? And so I'm not saying that this is the only way to do this, but I'm saying, you know, this is a way to do this, is basically to that gives you something gauge invariant, right, is to choose it to talk to, you know, the difference of these two, and then you get an action that's not 0, and that is gauge invariant. So I think at the lattice, I mean, yeah, so in the continuum, you can play around with A plus B and A minus, you know, taking sums and differences of things here. But at the lattice level, the fundamental thing that's trickier is, you know, the A's and B's just live on the same, you know, B's live on the dual lattice, A's live on the lattice. This model is self-dual under lattice to dual lattice, and there's just a very natural pairing between them. Yeah. Yes. That's right, yeah, yeah, and that certainly works very nicely for like subsystem symmetries in 2 dimensions, and yeah. Okay, well, so the elasticity stuff also comes from, you know, comes from a U1 theory, and here we're, you know, essentially this is Z2, so in that sense it's different, but also, I mean, this anisotropic model is not exactly dual to elasticity. Yeah, I mean, I mean, like, maybe one could think of a weird elasticity theory that had some but I don't know if that's useful. Yeah, no, so you can certainly think of that. I'm not aware of there being kind of literature on that, so I'm not able to comment. But yeah. Exactly. Yeah. So. Yeah, and Leo wrote sort of a series of papers on it. Yeah. That's right. I mean, there's another sort of connection with gravity, which is that if I sort of if I thought of, you know, I mean, you can, if you thought of AXY as, well, yeah, like, so you can think of it in such a way that you could, this theory is called a scalar charge theory. I only have one scalar parameter alpha. But if I said, well, maybe I have, maybe the charge is more like a momentum, right? So I have different, I have like a vector alpha. Then you can relate, theories of this type to, things that really talk about momentum responses in certain kinds of lattice systems. So that's also, but like, so it's a connection, but it's different because the charges are different because they have a vector-like nature. Yeah. Okay. Okay, good. So this is a comment that, there's a sense, and I will come back to these statistics in this model later on. Oh, I just erased them. Next lecture, but there's sort of a comment that, there's a sense in which you can write down Chern-Simons terms, okay? And there's a discussion here, and I'll, like I said, maybe give more examples in the context of symmetries next time. But it is a little bit different, yeah. Right, 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 right. Okay, so I think when you define the model on the lattice, okay. Okay, no, so for the continuum theory, like right away, just the gauge transformations do not have continuum-like rotation invariance. So kind of right away, there's a geometry built in here. So in that sense, it's not topological from the get-go. Like, that's even true of this action. And then here, I can't get rid of the lattice constant or the dimensional coupling constant, because I have to tell you how thick these ribbons can be. And so that's a further challenge. Yeah. So I think most people would be very happy with thinking about this as a continuum field theory. I think a lot of people would not be happy about thinking of this as a continuum field theory. But if you bring it back to the lattice, it has kind of a natural interpretation. Okay. Good. And so let me see, how am I on time? Okay, so maybe at this point I will summarize. I'm just going to make sort of another comment. Okay. So the moral of the story is, yes, we sort of have Chern-Simons-like terms. They're a little different, okay? But maybe they're interesting, and I'll come back to that thought. My third comment is, okay, sometimes we can't talk nicely. About continuum limits, okay? So I've focused a lot on this line-on, plane-on model, and I like this model because basically I can fudge back and forth, sweeping some details under the rug between, talking about continuum actions and talking about lattice actions. And, once we have continuum actions, there's sort of natural things we can play around with to, maybe make Chern-Simons theories and so on. But you have to be careful because not everything has a nice continuum limit. Okay? And so I want to take a few minutes to talk about this Sierpinski quantum spin liquid, okay? And what is different about that, okay? And so I didn't say much about this model last time, so let me tell you a few things about it, okay? So this is my AV term that lives at vertices. And at the plaquettes, I have something like this. So this is my B cube term, okay? And very similarly to the operators that move E and M around in my line-on, plane-on model, right? I have... So, okay, so basically, if I take the in-plane projection, okay, it looks like a triangular lattice, except that my spins, okay, my spin-1/2 degrees of freedom live only in the centers of the upward pointing triangles. That's all. So right now, just at the level of the lattice, this is nothing too weird. I just put only the spins on the up triangles. Okay, so, and now let me, okay, I will show you the fractal. Let me show you the fractal right now, okay? So let's ask, who creates E? Well, I can, just like in the line-on-plane-on model, right? I can move my E's up and down vertically by acting with strings of Z's. That's exactly the same, okay? And so now, but let me ask how I move them in plane. I'm going to just work with this projection in the plane. So I'm going to suppress the Z direction. We're looking at a single plane, okay? And so if I act with Z in one plaquette, right? I act with Z on a single plaquette. Okay, so now I've created, you know, I've flipped one X at each of the 3 vertices on the corner. So it lives at the corners of a triangle, okay? And so now maybe I can try to fix this. I could act with Z on another plaquette. So now I erase the red dot in the middle, okay? And now, you know, maybe I act with Z on the top, and I get something like this, okay? And basically, so you can keep playing this game, okay? And basically, this is sort of where the Sierpinski triangle fractal object comes in, is that if you make these bigger, okay? So these, like, I'm going to call them Wilson fractals, because they're certainly not lines, okay? These are the Sierpinski triangles, you know, generated by this rule number, whatever it is, cellular automaton. Okay, so these are the E's. The M's look very similar. So let me draw the M's, right? And so again, in the vertical direction, this is essentially exactly like the line-on-plane-on model. I'm going to act with X's in the centers of plaquettes, okay? And then remember, in the planar direction, okay, so I'm going to act with an X on an edge. Now, I'm going to suppress the vertical direction, so when I look in the plane, what it looks like, right, is it looks like I'm acting just on a vertex here. Put an X here, right? And then I'm going to create violations of cube terms in, you know, cubes that surround this vertex, okay? And so now we can play the same game. Well, you know, maybe I act with another X over here, okay? That's going to erase this guy. It's going to create a violation here and a violation here, right? And then, well, gosh, we can complete our triangle, right? And then, I mean, you can keep going if you want to, right? And so now I have, you know, this sort of triangle of defects here. Okay. Okay, so these are the fractals for E's and M's. And, you know, very loosely, the picture of why you have braiding between E's and M's is the same as the picture I drew for line-on-plane-on, right? Imagine that I have this, you know, E particle sitting here, and then I have some kind of, you know, in-plane operator that sweeps an M around, and basically it's acting on a sort of forest of edges, right? A forest of edges coming out of the plane with some X's, and these are going to hit at an odd number of edges, or they can hit at an odd number of edges depending on how I choose the trajectories, and that's going to give me the statistics, okay? So that part, you know, looks exactly the same, and so I might be tempted to, you know, sort of try and write down a BF theory, take a continuum limit. Maybe I could even look for Chern-Simons theories. And I think it's interesting to try to do that, and I'm not going to say too much about it, but let me just say something about the continuum limit. Okay? So okay? And the basic idea that I'm going to present here, I'm going to talk about it for this model, but the basic concept was sketched for a different, more complicated model called the HA code in a paper by Bomash and Barkeshli. Did I write down the year? I did not write down the year, but so they talk about sort of taking continuum limits, right? And so first of all, if I want to take a continuum limit, I want to define some kind of Gauss's law, okay? Now it's not so obvious. So to define, to start talking about my continuum limit also, and I want to sort of start taking derivatives, I really want to kind of go to a U1 type version of this theory. Where is the reference for that? Okay, so you can go to a U1 version. This is written out in a paper by Myers and Jane. UU. By these people, okay? And the basic idea is that, so now, just like I did in the line-on-planar model, right, I'm going to put some, some degrees of freedom here on these edges. And then they show that, a reasonable coupling to take for the U1 case, right, is basically cosine of theta 1 plus theta 2 plus theta 3, okay? Okay, and so, so that's sort of telling me that my orientation sort of looks like this, right? That I sort of am going outward in all of these directions, okay? And maybe to skip over some details, what you find, okay? So your Gauss's law that you would write down looks something like, so if this is R, right? So my Gauss's law, okay, looks something like E of R0 plus, and let me call this like L here, okay, plus L y hat plus E of R0 plus L over 2, root 3 over 2 L x hat, okay, plus a half y hat plus E of R0 minus root 3 over 2 L x hat plus a half y hat, okay. And what you find, and you could play around with different sign choices here, okay? But what you find is that in the continuum limit, right, with this sign choice, okay, I get something like 3e at R0 plus, this is L squared, okay, okay. So you get something like this. And the basic point is that, so this is different from the Gauss's law that I would get with the plus minus on the square. So there, Gauss's law does have two derivatives, okay? But here, there's sort of something a little bit more fundamentally challenging about this continuum limit, right? Which is that in my Gauss's law, I see different powers of L, which is, essentially the lattice constant, okay? And so here, it's really, even to define this Gauss's law in a nice way, it's really difficult. Like I have this scale in my Gauss's law. And the basic reason why this is that the gauge invariant operators are fractals, okay? And so there isn't a continuum theory, right? If I truncate, right, my derivatives, expansion, my continuum limit, to any finite order, right, it's only going to get the fractal structure, okay, out to some length scale. Okay. So mostly I wanted to point this out, right, that here, so this is sort of the outcome of comment 3, is that sometimes, okay, if we really wanted, so they talk about, like making, how to build up, in this paper here, they talk about, how to kind of build up a continuum-like version of Gauss's law that will resolve these operators out to some length scale, okay? But if you really want to get the theory at long wavelengths, right, we actually need to work on the lattice. Okay. So that's another, this is sort of another higher level of the lattice is really important for what's going on. Good. Okay. So just, yes, yes. Yes, good. So John is saying, well, like you could have a lot of complaints about the continuum limit, even in this line-on-plane-on model, because the number of ground states, when I do it on the lattice, cares about the lattice size, right? So yes, this is absolutely true. But I would argue that in things like the line-on-plane-on model, it can be useful to think about a continuum limit, and we can talk about these field, this BF theory is, is a topological field theory. You can talk about it as a topological field theory, and you can invoke subsystem symmetry and say, well, I just have to pick the size of my subsystem symmetry group, somehow. That's right. Yes, many operators to vanish, and I think like one perspective is to build in this subsystem symmetry structure when it involves planes or lines or nice smooth things that are not fractals, is you should basically put a foliation structure on your manifold. Okay, so that kind of yes. Sorry, the fractal, okay, the fractal dimension, well, so I would say like the fractal dimension, the fact that these Sierpinski triangles, are fractals, I view that as related to the fact that, I can't like write some nice continuum field theory. I need all of these orders. Although I can't make a precise direct connection, but I think it's, there probably is a nice way to say that. Yes? Okay. So yes. So let me maybe. So the question was, I've written E as if it's a scalar, but right now, like I could have done this one here, right? And I would have said, I have an E here, and an E here, and an E here, and an E here. I've also left off the, there's a DZ, EZ term, which is like the usual thing, you know, okay, which I've left off. But yeah, so here I'm just sort of saying like, you know, I'm sorry, this is the wrong picture. Let me draw the right picture. I'm saying I have a vertex, right? And then, you know, like if I look in plane, I have these, perfect, okay, I have these E's here, right? And in plane, I actually really do only have one component, and then the other one is the out of plane component, yeah. Yeah. Good, okay. Yeah, so, you know, I think the basic moral is that there are many, I talked about a couple of simple constructions, okay? But there are many constructions out there, you know, families of things you can build that have a fractal-like character for their operators. There are many things that you can build that have, you know, maybe a character a bit like the line-on-plane-on model. There are things that, you know, don't even live on finite dimensional, you know, manifolds, okay, but still have this kind of topological-like structure. And so I think it's an interesting thing to ask, you know, what does this teach us about, you know, sort of different alternative notions of like topological quantum field theories? Okay. Now, I'm going to end, I'm running a little slower than I thought, so I'm going to end with sort of a motivation for what I'm going to talk about next time, which is, you know, the other sort of aspect of going beyond just, you know, topological phases that I wanted to talk about, which is making some connections to symmetry, right? So we all already talked about the fact that gauging something, maybe a subsystem, symmetry gives us a possibly fracton topological order, okay? And we know, and I'll go over this, right, that when we think about 2 plus 1D, so the topological orders, right, so this gives us a sort of a connection, right? So in this direction, so it gives us a connection to phases in 2D with global symmetry. So in this direction, I'm going to gauge the symmetry. And in this direction, I will ungauge the symmetry. And I'll tell you how you might do that in a minute. And we can learn actually quite a lot about the different kinds of 2D phases that have global symmetries by thinking about the different kinds of, you know, topological orders in 2 dimensions, right? Right, so we can learn about, for example, 2D symmetry-protected topological phases from these topological orders, okay? And maybe to be specific, the kind of thought that you should have in mind here is, so obviously, you know, if I have a single Chern-Simons theory, right, that has a abelian Chern-Simons theory, okay? That has a chiral edge, it has a central charge. You don't need any symmetry to protect that. It is there, okay? And so when we say SPTs, we usually mean something that's a little more fragile, right? Which is that, you know, maybe I have a Chern-Simons theory here in one plane, let's say, and then, you know, somewhere else, I have a Chern-Simons theory with the opposite chirality, okay? And so now naively I have these counter-propagating edge modes, but of course this boundary can be gapped. Okay? But sometimes it can't be gapped unless you break a symmetry. Okay, so this is the kind of connection, that's particularly useful if we want to leverage our understanding of topological order to understand phases with global symmetries. And so next time I'm going to review how this works in 2+1 dimensions, okay? And then we're going to talk about what kinds of connections we can make, okay, between fracton phases, fracton orders, and something like SPT, or symmetry-protected topological phases, and I'm going to put an extra S in front of here, and this S is for subsystem. Because as we said, when we gauge and ungauge for fractons, we are gauging and ungaging subsystem symmetries. And so I'll show you how this works and how, some arguments that you can make of when these edges can and cannot be gapped. And then we'll talk a little bit about how to use the ability to write things like Chern-Simons type terms in some of these fracton phases to learn about subsystem symmetry protected boundary modes. So I'll stop there, and we still have maybe 5 more minutes for questions if people want. Yeah.
Questions?
Yeah, good. Okay, so basically, first we have to pick our boundary conditions. So I'm not going to give you a number. But basically, we're going to pick our boundary conditions, okay? And obviously, in the z direction, it's just periodic boundary conditions, and kind of that part is simple. But the part of counting the ground state degeneracy that's a little complicated is you have to ask whether you can sort of fit, one of these triangles into your periodic boundary conditions, right? So, these things have a sort of, in such a way that the corners all kind of annihilate. So they have a kind of a Pascal's triangle structure, and if I draw my triangles like this, I can get things that sort of look like this, right? But if I choose my lattice size wrong, maybe this hits here, right? And then I have defects that I can't get rid of. And so basically, okay, what I'm trying to say is, and Zhongwen Ha has like a really nice formulation. He counted the ground state degeneracy for the Ha code. I don't know if but he had a very nice polynomial formulation that allows you to just crank out, or allowed him to just crank out these answers. But so for the line-on-plane-on model, basically, as long as I choose strictly periodic boundary conditions, okay, if I make my system bigger, I get more ground states. It sort of grows like 2 to the linear system size, okay, with some coefficient. Here, right, because of the shape of these fractals, I could increase my system size by 1, right, and suddenly I have a unique ground state, right? And the Ha code also, like for the Ha code, like some of these ground state degeneracies are extensively large in L, and some of them are finite, okay, and it changes very wildly with the system size. Yeah, that's right. You would pick your geometry to pick some number of logicals. Yeah, and so I would say like this model, once you're working in 3D, this model would probably not be your top pick for a quantum code. You would be better off, and that's because these particles are very mobile in the z direction. So what you really want to make error correction easier is, in the plane, right, to get from having these 3 to having these 3, I have to go through an intermediate energy barrier, right? And to get them farther and farther apart, I do have to go through bigger energy barriers, bigger and bigger energy barriers. And so that maybe gives me a little bit of, it's not a thermally stable phase, but it's maybe has slower dynamics, okay? But for this guy in the z direction, the particles are just, going to kind of diffuse For the HA code, they're strongly subdiffusive, and so that, you'd probably do that. Yeah. The question is there a system size for which? And have, you mean, and have one of these operators be non-trivial with no excitations? Is that the question? Oh, okay, sorry. It's not, okay, I can always choose periodic boundary conditions, okay? But it might be the case, but what I want in order to have like more than one qubit is I want to be able, remember like in the toric code, right? Well, here's one, I always have like the trivial ground state, which is just, the thing that I get by, starting with a state that satisfies all the vertex constraints and then just, making this projector onto all the cubes, okay? But now, to get the other ground states, I can think of what do? I take some Wilson line, which is like pulling a pair of E particles around in this direction or this direction. And so here, in plane, the Wilson operators are these fractals, okay? And so if I choose my lattice size to be, like if I have it be, I don't know, 4 by say 3 or something like that, right? So maybe I have, I'm not sure that it's a good idea for me to try to do this like live at the board, but okay, so now, so now we can see that, so maybe I, maybe I make a, something here, right? So the triangles are here, so I get defects here, here, and here, right? And then I can sort of, I can heal these ones in this way, right? And now I have to, but I sort of have to be able to kind of push it all the way up the system. And so it could be the case that it sort of, it makes this triangular shape, and it could be the case that that it just sort of, that I have a way for the top of the triangle to annihilate against something on the bottom, but that's not always the case, okay? So if I choose the system size wrong, then it's just gonna leave you some defects. Yeah. That, good. So I'm gonna, yeah, so I'm gonna talk a bunch about that next time. So I think let's hold that question. I will say that you can, chiral in the sense of their transport of U1 charge, I would say there is an analogy. Chiral in the sense of like a central charge thermal hull, not so clear. And we can talk about that later. But yeah, it's a good question. Mm-hmm. Okay, so typically, okay, so there's sort of two different things, okay, that you can play with translations and rotations. So one is like there's work by Shreya Pai and Mike Hermele where they tried to define some notion of like something like a fusion category for these guys, right? And so there's a notion of super selection sectors. Maybe let me just draw the plane, okay? And again, we'll suppress the z direction, right? But basically, like a dipole here can only move in this direction, right? So for the toric code, if I put an E here, right, I have a Wilson line that could move it anywhere. So all of the E's are sort of like in the same super selection sector. The theory is topological. On the other hand, if I have a dipole here, that's actually not the same as having a dipole here. There's no, kind of line operator that can translate them. So this is the sense in which, sort of translations are very, very different here. But the other thing that you could think about, although I don't think this is what Pretko, I don't remember reading about this in Pretko's papers, but the other thing I could do is just in the toric code, right? I could, for example, take the toric code and say, well, instead of having this product around the boundary of a plaquette of sigma z is +1, let me choose a Hamiltonian where it's going to be -1, right? And now the E particle, as it goes around the plaquette, it's going to pick up a Berry phase, and so now the E particle has some, non-trivial transformation under translations, and that you could do here, I think, in the same way. Oh, you mean like this Q of X? Yes. What do you want to do with this algebra? Yeah. Yeah. Okay. So I don't. I think so, but this is not something I've thought about. So maybe I won't make a definitive comment. But there's certainly there's work by Andrei Gromov, for example, where he defined this thing called the multipole algebra, right? And it's related to these higher conservation moments. And yeah, so that's certainly relevant. If you want to describe subsystem symmetry and this kind of restricted mobility, there is a multipole algebra that you can associate with that. That's certainly true. Like for the non-abelian thing. Right. I can write down okay, let me write down.
Actually, in cases where there is an energy elasticity, that might happen because
So what you want, let me make sure I understand the question. So the question would be something like, I want to have some line operator that's only allowed to move in this way, associated with, subsystem symmetry, and I want to have another line operator that's only allowed to move in this way, such that these two don't commute. Is that what you're asking about? Yeah. Yep. Yes. No. Would you like me to write? I can write down a model, but it will take a few minutes. Should we? And I was going to say, maybe this will take a few minutes. Maybe people who want to hear it can stay, but maybe people who don't, because it's a significant digression. I can write down the model, but maybe other people can leave if they want to.
people are always free to leave.
Are there other short questions before I do this? Yeah.
Thank her, and then will people
Yeah.